Thanks for your patience with the internet issues this week. So as promised, here's a video going through a couple of these examples we started to go through. Okay, so in these sketch the signal examples, first consider these 2-point objects, some location. All right, and I'm gonna change from the notation I used before and refer to this one as x1. One here. And so I'm going to determine the signal that we're going to get. Hey everyone, as promised, thanks for your patience, and I wanted to go over these examples that we started to go over in class before getting a little bit interrupted. So here we want to consider this this object consisting of these two locations in X, and figure out what the received signal is going to be from these two objects. And I think it'll help if we look at the transverse magnetization of these two locations, and let's give them their own colors here to help us out too. And so what, and let's map out the net magnetization at a couple of different points in time. As we've done before. And let's use the top here for the top pulse sequence. And same with the bottom sequence. Okay, and in these plots, it's going to show MXY for time 1, 2, 3, and 4. And so tip these, both cases, tip the net magnetization into the transverse plane. In the top sequence here, when there's no gradients applied, we have no phase accrual, we have no change in frequency. So at time point 2, there's no change in the net magnetization. But then at time point 3, we're going to get to the case where we're going to introduce some rotation because of the position in X here. So we have an X gradient on. So might create some net rotation to some angle here, and continue on to a later time. This X1 position continue to rotate some angle phi, and our other position, the minus X1, also tipped by the RF pulse, nothing happening during the first interval there. It's going to rotate the gradient in exactly the opposite direction. So phase angle here is going to be gamma times the readout gradient amplitude times the position, so minus x1 times time, and same thing for the phase of angle of our other location, except it's positive x1. Where here we're defining this time here. Or annotate up here is time is 0 here for that t variable. And then recall what the signal is it's going to be the sum of both of these transverse magnetizations. So the signal, this is going to be the sum of, and you can just color code it, of this location plus our other location that are always going to be pointing in the signal is the sum across the coil. They're always going to be pointing in these opposite directions. What this means is that the y component, which is our imaginary component, cancels out, and we end up with this sinusoidal oscillation. So we tip the net magnetization, we create some signal, these two vectors add together, then as they spread apart from each other, the signal is going to decay, and as I've drawn it, you can see actually these two vectors would at some point 0.90 degrees from each other cancel out sometime in between time 2 and 3. And it can actually derive that the shape of this curve is going to be a cosine of the same form of gamma gradient amplitude times the x1 position times time. And the other interesting thing we can think about here is, well, if we take the Fourier transform of this expression, turns out this is equal to a delta function at a frequency of f minus, and it turns out to be, it's a good exercise to go through this Fourier transform. And I can add the 1/2 right now. F minus this this term, so it's going to be an f minus a gamma bar gxr x1 plus an additional delta function here of f, and it's going to be plus gamma bar times the gyromagnetic ratio times x1, the bracket in there. So what this, the image, or we take the Fourier transform of the signal, what we're going to get is basically our nice point object at plus and minus these values. So this is actually what we should get when we take the Fourier transform of our signal. We should get back our original object. In this case, we do. And then turns out for the second example here, it's going to be exactly the same because there's no, the y gradient here creates phase that's dependent on the y position. There's no change in the object in y. So all these here are the same as above. Now, if we go to this object where we had now an object that's existing along the y dimension, and let's go ahead and look again at several times. And what we're going to see is in the first case here, since we have no gradient in y, there's going to be no effect of the gradients. So if we did repeat these drawings of the net magnetization and then sketch it out quickly on the bottom here. That in the first case, we tip our net magnetization, and since it's at a position of 0 in x, there's no effect of the x gradient, or the frequency is dependent on the position in x. The position in x here is 0, so there's no effect there for either one of these. And remember, our signal here is going to be the sum of these two. So we're going to get just this constant signal after our pulse, we tip the net magnetization into the transverse plane and get just the constant signal. Now, once we apply a phase encoding gradient down here, then this is, and it's in the y direction, so it's going to have some net effects on this object. Tip our magnetization down, and it's going to be rotated by some phase angle here. It's going to be equal to the gyromagnetic ratio times the gradient area times the position y1. And then after that y gradient is turned off, it's just going to stay at that same position here, because just like the example above, the x gradient has no effect at x equals 0. And then our other part of our object here rotates exactly in the opposite direction by exactly the same amount in this setup. Because it's at negative y1. So it's going to be at the same negative phase angle here. So what I'm drawing here is saying, well, if this gradient amplitude is GYP for GY phase encoding, if the duration here is TY, then at this point, the phase of net magnetization at time 2 is going to generally be gamma times the gradient area times the position in y. So this, our gradient has turned on. It's created some frequency change for some short amount of time. Then it's turned off, and it's created this phase angle for these locations. So in this case, we'll excite. The signal will add coherently. Then as these two spins accumulate phase, they're going to start canceling part of each other out. as I've drawn it, it would go to some position like this where they've largely canceled each other out, but there's still some net signal. And then they stop at this position. There's no additional phase accumulation. And then it's constant again over this interval of the readout gradient. Now, this case is a little bit more complicated, although here we're just going to look at the X contribution here. So we can look at this now in a little different way. So for the top example here, where let's look at the relationship here that we're going to create of frequency versus the X position. And we create some, say it's some amount like this, where let's again call this GXR, and if we call the frequency this time is gamma bar times GXR times the position X. So what we can see by my, maybe we can see, but my crude drawing here is that one edge of this rectangular object is going to map to this range, this value in frequency, and the other edge of the rectangular object is going to map to this value in frequency, and we're going to get everything in between. So if this value over here, say, let's call it W over 2 and minus W over 2, that then we're going to get a range of frequencies. This frequency here would be minus gamma bar GXR W over 2, and similarly this value up here is going to be positive of the same quantity. So our signal here is now going to be a sum or an integral of all these different frequencies going from this range. I'm going to write it out precisely, but I'm not going to derive it any more precisely than this at this point. Okay, it's a sum of across this range of these net magnetizations rotating around, so these complex exponentials. Integrated over this frequency range. So basically the sum of all these different frequencies. And what we learned from our RF pulses is that actually this relationship, this expression here is going to give us a sinc shape. This is in fact where the sinc function comes from. It comes from the adding together over a limited range of frequencies. So we'll create some excitation, and then the pattern, oops, we would get here be like this sinc pattern in our signal. And the other way that we'll start to use to figure out what this, understand what the signal would be, or the impact, is actually, well, if we take this signal and we apply Fourier transform, what do we get back? And we get back a rect function, right? Some rect function here. And you should look at our object and go, aha, this is what we should be getting. We have a rect function in the x direction. So when we apply frequency encoding and then Fourier transform that to get our image, we should get back a rect function in our, this is like our reconstructed image over here. And then what happens in the bottom example is a nice illustration of changing gradient amplitudes, where now we have a stronger gradient on, let's say it's, could be anything, let's say it's twice as strong. So now this line is like strong, has a higher slope, and the range of frequencies that we're going to get is going to be larger. So we're going to go from a range of twice what we had before. Or again, we're going to get a sync shape, but I can think of this in a couple ways. One is that we have higher frequencies. This is going to be a higher oscillation in our sync function. So we should get a sync function that's in fact going oscillating twice as fast as we were before. So this is again a sync shape. And again, if we take the Fourier transform, we try to draw this sort of a little bit of a sketch, but relative to the top picture there, we should get actually a wider rect function. And what this corresponds to, like this, we have a wide range in frequencies here, which corresponds to this wide range of frequencies that we encoded into our object with our frequency encoding gradient. And similarly, this narrow range of frequencies we see in the Fourier transform of our first case corresponds to this narrow range of frequencies that created in this object with the lower readout gradient amplitude. Okay, so hopefully that helps you understand a couple of those examples.